All right, another video on limits. This is infinite limits and limits at infinity. So some of these limits you've kind of already talked about have to do with asymptotes and some things, and so we're just going to formalize them a bit and connect that, and again, better with the limit notation. So I'm going to talk about what happens when we go towards infinity, and also when the function, like how the function works as we go to infinity, and when the function tends to go to infinity on the function. So those are the things that we're going to look at. So we're going to look at these two, these functions. So we're going to look at this function first, the f of x, and we're going to look at what's happening at various places to talk about that, that type of limit. All right, so first thing we want to look at, looking at it from the graph, is the limit as x approaches 4 from the left. And remember, just always say it that way in your head. Limit as x approaches 4 from the left. Never say 4 minus or any of that. It's just limit as x approaches 4 from the left of f of x. So we just go to the graph, and we literally just approach 4 from the left. So we're on the graph right here. We're approaching 4 from the left, and we can see that we're going to infinity. You don't have to write a plus infinity. You could just write infinity. And then we look at the next one, says what's the limit as x approaches 4 from the right. So now we go to the right of 4 and follow the graph. And so as we're coming towards 4 from the right, we're going to minus infinity, and you do have to, of course, put that there when you have minus infinity. And then we want to answer what is happening as we approach G. So this is not this graph. We need to go to G and look at what G is doing as it approaches 1 from the left and from the right. So as we approach G, or positive 1, so as we approach positive 1 from the right, we're going to be going to positive infinity. As we approach positive 1 from the left, we're going to be going to minus infinity. So back here, as we approach 1 from the left, we get minus infinity, because on the left side of 1, it's going down. And as we approach 1 from the right, we're going to get positive infinity. Okay? And so what we discovered is that a vertical asymptote will approach either positive or negative infinity, because both of those were vertical asymptotes. So they will approach either plus infinity or minus infinity, and that's what happens when we have a vertical asymptote. Okay, so it will occur if the one-sided limits are unbounded. So at a vertical asymptote, as we approach that, I guess we should say as we approach. Okay, so as we approach a vertical asymptote, we will approach either positive or negative infinity. So as we go towards that, that's what we're going to have. All right, so now let's look at, so this one is asking me to go back and look at f and g also, but this time my limits are what is happening as x goes to minus infinity or as x goes to plus infinity. So let's go back to f. So now what we're talking about is what is the graph doing as we go to the right or to the left? And when we say the right or left, we mean way to the right. So we're going way to the right. What is the graph doing as I go to positive infinity? Well, it is approaching this negative 2. So the limit as I go towards negative or positive infinity is negative 2. If I say what is happening as x approaches negative infinity, that means I'm going to the left. So if I just keep following the graph to the left, I'm also approaching negative 2. So both of these are going to be negative 2 for f. Now looking at G, what is G doing as I go to minus infinity is the first one. Well, now I'm going this way. Well, now look what my graph is doing. Well, it's not approaching a single number now. Now it's actually going down. So it's going to minus infinity. Eventually it just keeps going down, 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 and it's going to minus infinity. As I approach positive infinity, so going this other direction, again, the graph is going up. Now it's going up slower than if it was at a vertical asymptote, but it's still going to infinity. And so we call that a slant or an oblique asymptote. This one here, the graph is kind of looking like it's flattening out like a line, but it's a slanted line or an oblique line. So that's called a slant asymptote or an oblique asymptote. And you can either go towards that or a horizontal asymptote as x approaches in these. So as x approaches plus or minus infinity, these had a horizontal or a slant asymptote. Now that's not true for every function, but it was true for these two. Okay, so basically, for these rational functions, that's true. So an infinite limit is as x approaches c, so some number, the limit will approach positive or negative infinity. So that's an infinite limit. And so generally a vertical asymptote would be there. A limit at infinity is talking about as x approaches positive or negative infinity. So it's talking about what happens as I go to infinity. So the limit will either, the only two choices are, the limit will approach a y value. So it will either approach a y value, like, and have a horizontal asymptote, or will be unbounded. So when you get an answer of infinity, so when we talk about the limit equaling infinity, we're saying that it's unbounded. So it's going to infinity is unbounded, because again, that's like the ceiling. I have no ceiling, so I have nothing that stops me, so I'm just unbounded. Okay, so you had this in pre-calculus. We talked about what would happen and when you had a rational function. Again, this is true for rational functions, not every function, but for rational functions, if you could factor something and cancel them from the denominator, so, and you could cancel it out, you would have a hole in the graph. And if you had could not cancel a factor out, you had a vertical asymptote. So basically, I think your paper shows it different. So we basically have case number, this is case number 2. You would have a hole in the graph. So this would be a hole occurred. So this is when you have, remember, 0 over 0. And then if you have non-zero over 0, then you would have a vertical asymptote. Again, only for rational functions. You may not get that situation for other type of functions, but for rational functions, for sure, always that. So here we're going to figure out those limits analytically instead of doing them the way that we did it there. So we're going to figure out, like, just by looking at the graph, what would we end up with? Okay, so if I take the limit as x approaches 4 from the left, and this was the first function we looked at, what we would do if I just gave you this problem, you would not want to necessarily graph it. You would want to analytically figure out what's going on. So you would want to factor the top and factor the bottom. and see what you get. Now, what I would do is I would do scratch work, always way over to the right, do some scratch work, and I'm going to do the scratch work to factor the top because I really need to do two things. First thing, factor out -2. There's a 2 in common in everything, and we definitely want the x squared term to have a positive in front of it. So I'm going to factor out -2, which is going to give me this. Don't forget, every time you factor in your head, distribute and make sure that all of your signs and everything match up. And so everything's correct here. Then I would factor the inside factors of -6 that add to 1, because that's a 1 in front of this x, right? When it's just plus x. So that would be +3 and -2. So now I'm going to come back over here. This is -2 times x plus 3 times x minus 2. The bottom one is a one-step factoring because a is 1. So I need factors of 8 that add to -6. So that's going to be -4 and -2. So x minus 4, x minus 2. Now, because I'm doing limits, I can cross this off and keep the equal sign because I know that these limits are equal. The functions are not. The function before I cross stuff out has a hole in it. The function after I cross stuff out does not have a hole in it, but I can still look at what's going on here. So that means first thing I do to do a limit is I would plug in. So I would plug in 4. If I plug in 4, I get 0 in the bottom, not 0 in the top, which means there's a vertical asymptote here. So all I need to know, is it plus infinity or is it minus infinity? That's all I care about because I know it's one of the two. There's a vertical asymptote. This limit is going to plus infinity or minus infinity. No options here. So all I'm doing is looking at numbers to the left of 4, so like 3.9. If I plugged in 3.9 right here, the bottom is going to be negative. If I plug 3.9 in here, the top is going to be positive inside the parentheses, but negative because of the negative in front. So I'm going to have negative over negative, which is positive, so I'm going to get positive infinity. And of course, we see that from the graph, but this is how I would do it analytically. Now, when I want to approach 4 from the right, well, we just did all of this factoring and everything, so I'm just going to write down what we ended up with, which was -2 over x plus 3, or times x plus 3 over x minus 4, after we factored and divided stuff out. Now pick a number slightly to the right of 4, like 4.1, and plug it into both of these places. So you're going to get positive on the bottom, and then positive inside the parentheses, but you're going to get negative from the -2, so this is minus infinity. So analytically, I need to know there's a vertical asymptote there. I just need to know positive or negative, okay? So then let's look at C. So same idea. I'm approaching from the left of 1. So I'm going to see if I can factor the top. Well, guess what? Can't factor the top. I need factors of 5 that would add to -2. Those don't happen. So this doesn't factor. The bottom factors, not much, but it does factor out of 2. If I plug in 1, I see that I get 0 on the bottom, and I'm not going to get 0 on the top, which again would tell me, even without a graph, I have a vertical asymptote here. So all I need to know is, am I getting positive or negative? That's all I care about. So plug in a number slightly to the left of 1 and see what we get. So on the bottom, it's very easy to see I'm going to get negative because you're going to plug in a number just a little bit less than 1, like 0.9, and 0.9 minus 1 is negative. So the bottom is negative. Then I have to figure out the top. Well, the way I look at it is you don't have to actually do all the arithmetic. You just have to figure it out a little bit. Well, I pick a number less than 1 and I square it. So I'm going to get something even smaller than 1, right? Because numbers between 0 and 1, if you multiply them by themselves, they get smaller. So this is even less than 1 minus 2 times something a little bit less than 1. So this is less than 2. So I have something less than 1 minus 2. or something a little bit smaller than 2, I'm not going to get anything bigger than -5 here, and I have to add to 5, so I'm definitely getting positive. So I don't need perfect, I just need to know, is it positive or negative? And in other words, this term right here, I can't get big enough to cause the top to be negative. I'd have to overcome the +5 and the number in front. So definitely positive over negative, so this is negative infinity. And then we do the same thing for this one. So again, imagine it factored. Now, why does factoring help me even though the top doesn't factor? Well, it's because I'm trying to figure out the sign, positive or negative, and notice it's so much easier on the bottom because it does factor. But same argument here, except the bottom now is positive because a number bigger than 1 minus 1 is certainly positive. And then the top is going to be positive. So this is going to go to positive infinity. And if you look back at the graphs, you see that that's what's going to happen. So here's where we have our non-zero over 0. So we know that here we have a vertical asymptote. If we have a rational function and we get non-zero over 0, if we get 0 over 0, this is the location of a hole. Okay, and so that's what we want to do for dealing with our asymptotes, or that's how we previously did. Now we have to say it a little bit different because we have to use calculus to talk about it. So what we want to say is to get a vertical asymptote is we would say if the limit as x approaches c from the left of f of x equals plus or minus infinity, or same thing for the right. So c approaches, or x approaches c from the right of the function, and you get either a plus or a minus infinity, then we know that x equals c is a vertical asymptote. And this doesn't matter if it is rational or not. And that's the advantage. So now, if you're approaching a number on a function from the right and the left, or the left, and you get infinity, then you know there must be a vertical asymptote there, okay? All right, so removable discontinuity. So again, it's removable if you have a hole, because it's like a pothole where we can just fill the pothole in and the street stays the same. So here we're going to find vertical asymptotes, and then we're going to justify it by limits. So what we would want to do in order to find our, whether we have vertical asymptotes, is this is a rational function. So we're going to factor the top and we're going to factor the bottom, and then we're going to look and see whether we have any factors that cancel. So in the top, you're going to have factors of -10, that add to 9. I have no choice here but that, so -10, I need them to add to 9, so that means I'm going to have 10 and -1. So 2x and x is the only way I'm getting 2x squared if I'm going to use positive integers. And then my outside product and my inside product must be these two numbers, ignoring the x part, the coefficients work that way. So I can't take 2 times an integer and get -1, but I can take 2 times 5 and get 10. So there's my 10, and then here is a 1, right? This in front of the x is a 1, and I need to make a -1, so 1 times -1. So that's just a quick review of factoring. You need to continue to work on that. The bottom one factors much quicker because a is 1. You just need to find those factors. So what would happen here is you could cross these off, but as soon as you cross them off, in order to keep the equal sign there, you need to say as long as x doesn't equal -5, okay, because I can't cross stuff off and say it's equal. The limits are equal, the functions are not, okay, they're similar, but they're not. So now I know that there's going to be a vertical asymptote at x equals 2. Because the top will not be 0 and the bottom will be 0 there. Now, how will I prove that? So I would say at x equals 2, there is a vertical asymptote then I give my reason. So in calculus, you have to learn to justify a lot. So my reason is because the limit as x approaches 2 from the left of h of x is going to be either positive or negative infinity. So let's figure it out. Well, again, I only have to look at what's happening here, honestly, because the sign isn't going to be any different whatever I plug into the x plus 5 and x plus 5, right? So that's not going to change the sign of my problem. So pick a number slightly to the left of 2, like 1.9. Your bottom will be negative. Your top will be positive. And so you're going to get minus infinity. And then if we take the limit on the other side, so we want to also check that, the limit as x approaches 2 from the right of, and the function was called h. If we go from the right, you're going to get positive on the top, of course, 4 minus 1. If you pick 2.1, you're going to get more than 1 minus 1. And then the bottom would be something bigger than 2 minus 2. So you're going to get positive infinity. So now I've justified it, okay? So that's the calculus manner. We've got to justify it. All right, so let's do a couple of limits at infinity, and then the rest of it we can finish in class. So find each limit at infinity and give your reasons, okay? So this is end behavior. So this goes back to pre-calc when you talked about end behavior. So if you look at this graph, the end behavior, so end behavior meaning what's happening as I go to infinity? Well, when you have polynomials, which this is a polynomial once you multiply it all out, all you had to look at was the highest powered term, because that's what was going to determine your end behavior. Well, this is a quartic of 4th degree, and it's positive in front, which means that both ends of this are going up, if you remember your end behavior. So you're going to have both ends up, so therefore this is infinity. And so the explanation of your thinking would be that this is a quartic, and it's positive in front, so both ends go up. And that's what you would write to explain your thinking. Here, we don't have to multiply it out. We see that we have 3rd degree. And remember, on 3rd degree graphs, they either go up to the left and down to the right, or they go down to the left and up to the right. Those are your only choices. Well, this one has a positive in front, which means it's this case. So as I go to minus infinity, that means it go to the left, I'm going to get minus infinity because the left side of this graph goes down. So let me write this explanation out. A cubic function with a positive leading coefficient, that's the 5, just means the one in front of the largest term there. Positive leading coefficient falls as x goes to minus infinity. So then that means that f of x goes to minus infinity, okay? So that's an explanation, putting a little bit of calculus in it. Here, your explanation would be, so remember this, even as far back as algebra 2, you're going to infinity. This is a rational function, so we only need to look at these two terms. You have 3x squared over x squared, so this is going to go to 3. And that's because the powers are the same. When the degrees equal the same, you just need the ratio of the coefficients. Here, I'm going to minus infinity of a rational function. Again, I only look at the leading terms because the other terms become insignificant as I go to infinity. Here, you're going to have the bottom being much larger than the top. And so this one is going to go to 0. And that was when the degree on the bottom was greater than the degree on the top, you're going to get 0. Okay, so let's look at just a little bit of this explanation of the different things that can happen here. So there's really only 4 possible outcomes when you go to the right and the left. So the curve can increase without bound. So we can have the limit as x goes to infinity of f of x is infinity, okay, because you're just going up. The curve can decrease without bound. So here's an example of a third degree equation, possibly, and it's going, as you go to the left, which is like the example we looked at, it's going to minus infinity. You have this example that as we go to infinity, it can be approaching zero. So this is, again, as I go to infinity, I can be approaching zero, okay, can be asymptotic to the y-axis or to any other place, but that's what we'll see next. The other option is the curve can go specifically to a value, okay, like you can imagine there being a horizontal asymptote here. You can see it flattening out. So those are the 4 possible outcomes as you look to the right and left. It either goes up, it goes down, it goes toward the x-axis, or it goes towards some other horizontal line. That's the only possible manner. Okay, so this is kind of a revisit if you need to look at that. This is the how you do the horizontal asymptotes about the degrees of numerator and denominator. So look through that, and then the rest of the examples we can do in class.